Hello, and welcome to this presentation introducing my team's work, FUSE, Fast Unified Simulation and Estimation for PDEs. This work focuses on exploring the relationships between finite and infinite dimensional spaces to aid our understanding of complex systems and their uncertainties. But before we dive into complicated sets of equations, let's start with something a bit simpler. Consider the linear equation y equals mx plus b. Here, m and b can be thought of as parameters which define some rule relating x and y. Knowing this rule and following it is known as the forward problem. Alternatively, having data described by such a rule and trying to re-estimate these parameters is known as the inverse problem. For simple sets of equations, this is not difficult, but consider a higher dimensional problem described by a set of partial differential equations. Here, we can have strongly nonlinear relationships, and it can be very difficult to solve both the forward and inverse problems. If we consider something such as the wave equations, we may be able to make a prediction, but it's likely that there is some error associated with these predictions. Ideally, we would like to estimate these errors and understand their source. Is it due to uncertainty in particular components of the system itself, or does it come from an error within our model? In this example, the wave equation is parametrized by wave speed, c. Predicting the wave dynamics of our surface is fundamentally tied to this parameter, and requires at some level an implicit estimate of its value. But some values of c may result in greater levels of uncertainty than others. Looking at machine learning-based approaches to solve systems of parametrized PDEs, we see neural operators are capable of impressive results, but they lack this fundamental ability to tie the results to the physical parameters defining the system. So our foundational question for this project was, can neural operators be modified to provide estimates over finite dimensional values as well as infinite dimensional functions? To answer this question, we propose FUSE. This model functions somewhat similar to an encoder-decoder. To handle infinite dimensional inputs and outputs, we use the lifting, projection, and operator layers of a typical neural operator. However, in the middle, we rely on the space of band-limited functions to learn a map between finite and continuous data. Likewise, we use a probabilistic posterior estimator to learn a distribution over the PDE parameters, as opposed to a single deterministic estimate. This distribution can then be pushed through the rest of the model to provide interpretable uncertainties on the output functions. Let's investigate the performance of this model for a problem from weather physics, known as the atmospheric cold bubble. In a field of ambient air, an elliptic mass of colder air appears. Due to its higher density, it sinks down to the Earth. We collect data on the air velocities in time at the locations marked by the black triangles. Although the dynamics of this system may be very complex, they are fully described by 6 parameters, namely viscosity, diffusivity, amplitude, width, height, and altitude. Unifying the forward and inverse predictions, we observe how some parameters may be estimated with great accuracy, while others, such as diffusivity and viscosity, often have larger uncertainty ranges. Nonetheless, larger errors in estimating these parameters generally does not result in much difference over the estimated velocities. The uncertainty range, highlighted in red in the plots on the right, still contains the true solution, even when the estimated solution deviates from this value. Beyond that, a trained model can work as a fast surrogate. This allows us to explore the parameter space and observe the effects of each of the parameters on the velocities. Thanks for checking out this video. If you're interested in running the models yourself or reading the paper, you can find those at these links.